All right, this is Energy 5. Go through these problems, see how it goes. A student eats a tasty school lunch containing 700 calories, and we saw that in another sheet recently. One food calorie is 4,186 joules. Due to basal metabolism, that means just like your metabolism when you're just sitting there, not like running laps or anything like that. The student radiates about 1,000 joules per second into the environment, mostly as heat. How long would the student have to sit on a couch to radiate away all of the energy from lunch? Well, if we've got a 700 calorie lunch and it's this many joules per calorie, multiply those together. 700 times 4186 is about 2.9 million. That's how many joules. And they're doing this many joules per second, so if I divide by 100 joules, that gives me 2.9, that's joules per second. 2.9 times 10 to the fourth, right? Divided by 100 is going to knock that down by 2. That many seconds. And if you want to, you could like convert that to something that is a little bit easier to understand. That's a lot of seconds. So that's how many seconds. If you wanted to change that to hours, you divide by 3,600, so about 8 hours. Now, of course, you burn calories faster than that because you're not sitting on a couch for that whole 8 hours. You're like walking around and doing other stuff. But if you do, like just your base metabolism there, if you multiply this by 3, 8 hours times 3 is 24 hours, then that's your 2,100 calories, and they recommend people have like between 2,000 and 2,500 calories a day. So there you go. The math checks out. If all the energy from the student's lunch did something useful, like lifting pianos weighing 5,000 newtons to the top of a 10-meter tall apartment building, how many pianos could you lift with the energy from lunch? And we're ignoring that the energy is radiated. We're going to use that energy. So let's see. So how much energy does it take to lift one piano? So before the piano gets lifted, it does not have any piano. Before the piano gets lifted, it doesn't have any gravitational potential energy, and then after it does. How are we going to lift them? Well, this energy is going to come in and have work coming in here. So let's just do this for one piano. So how much is it going to take? So 5,000 Newton piano, if it weighs that much, that means it's 500 kilograms. Just going to make a little note of that. So the work for one piano is equal to the gravitational potential energy, which is 10 times mass times height. So that's 10, that's 100, that's 500, so that's going to be 50,000. 50,000 joules. And how much energy did the student have? They had this much energy, so 2.9 times 10 to the 6 joules, and then that's how many 50,000 joules per one piano. So if I divide the 2.9 times 10 to the 6 by 50,000, that's going to give me how many pianos? 2.9 times 10 to the 6 divided by 50,000, about 58 pianos. So what does all this mean? You're like, wait, this one school lunch, you could lift 58 pianos up 10 meters? No, this is just, I think if you're going to take away anything from this, it's that the way that our bodies use energy is pretty inefficient. It's very good at keeping us alive, all our metabolic processes that have to happen for us to keep on ticking. But like to purely transfer that energy and to do something useful, it just shows us how much energy really we are using all the time. 58 pianos lifted 10 meters worth. All right. Number 2, Jill pulls on a rope to lift a 12-gallon pail out of a well while Jack watches. For a 10-meter segment of the lift, she lifts the bucket straight up at a constant speed. How much power is required to complete the task in 5 seconds? Okay, so real similar diagram here. There's the bucket of water and the entire earth, and Jill is going to I'm going to put her outside the system. She's doing work. It's the work done by Jill, and that is lifting the bucket. So the work done by Jill is equal to that gravitational potential energy. So let's see, work done by Jill is equal to the gravitational potential energy change. That's M mass is 12 times 10 times mass. I usually write those the other way around. Doesn't matter because it's a multiplication. But 10 times mass times the height is 10 meters. That's 1,200 joules. And then the power is the work done by Jill divided by how much time it takes. So that'd be 1,200 joules, and she's going to do it in 5 seconds. It's 240 watts of Jill power. All right. Hulky and Bulky are 2 workers being considered for a job at the UPS loading dock. Hulky boasts that he can lift 100-kilogram box 2 meters in 3 seconds. And then Bulky counters with a claim of 200, 5 meters in 20 seconds. So which one's more powerful? So power is equal to work over time. And the work, just like the last 2 problems, the work that they're doing is the gravitational potential energy, right? In both of these cases, the work is changing the gravitational potential energy, and that's 10 times mass times height. So for the power of the first dude, Hulky, is the gravitational potential energy, which is 10 times mass times height, right? So 10 times mass, the first dude is a 100-kilogram box, times the height is 2, divided by time. And for the second guy, he is lifting a 200-kilogram box, so 10 times 200, and he's lifting at 5 meters, and it takes him 20 seconds to do that. So let's see if we can get that power rating for both these guys. So 10 times 100 times 2 divided by 3 is, this guy's about 670 watts, and this guy is 10 times 200 times 5 divided by 20. This guy's about 500 watts. So, which worker is more powerful? This dude. Not by a whole lot, but a little bit more. The trains on the Boss roller coaster are raised from 10 meters above the ground at the loading platform to a height of 60 meters. So notice that that's a change of 50. at the top of the first hill in 45 seconds. Assume that the train, including passengers, has a mass of 2,500 kilograms. We're going to ignore friction. How powerful should the motor be to accomplish this task? So at the beginning, I've got a little bit of gravitational potential energy, like 10 meters worth, and then the end got 60 meters worth. So where's the rest of this energy going to come from? Well, the motor is going to have to do the rest. Right? So my energy conservation equation is just showing that these two sides are equal, right? So Eg at the bottom plus, this one block plus those 3 blocks equal to the Eg at the top. Right? So that Eg at the bottom is 10 times mass times height, which is 10 at the bottom, plus the work done by the motor is equal to, at the top we got 10 times mass times the height at the top. So the work done by the motor is let's see, is that 1.25 million? 1.25 million joules. And the power, how powerful should the motor be? The power is equal to work divided by time. So that's 1.25 times 10 to the 6 joules of work, and we want to do it in 45 seconds. So this is our new move, right? We knew how to do everything up to that point already, and now we're just saying, oh, well, if we want to know power, we just divide by that time. So that divided by 45 is about, I'm going to round that up to 28,000 watts. So you could, if you wanted to, it's 28,000 watts. You could call that 28 kilowatts, if you want. Number 5, an aerodynamic 1,000 kilogram car takes about 270 newtons of force to maintain a speed of 25 meters per second. How much horsepower is required from the engine to maintain this speed? So we'll figure out in watts first. Well, remember that power, one of the ways of doing it is equal to force times velocity. That's the easiest way to do this one because we have the force and velocity right there. So 270 times 25, force is being measured in newtons, the speed's in meters per second. That's all the correct units that I need. So 270 times 25 is 6,750 watts, and then 1 horsepower is 746 watts. So I can use that as a conversion factor, right? So 6750 divided by 746 will give me, that's about 9 horsepower. How much horsepower is required for the same car to accelerate from 0 to 25 meters per second in 6 seconds? This is a little bit trickier. So I need to find that acceleration first, so that I can do force equals mass times acceleration, and then I can do this again. Or you could do, let's do it this way. What is the change in, the thing that's getting changed here is the kinetic energy of the car, right? it's going from having none when it's going 0 to having 25 meters per second worth. So the change in energy is equal to 1/2 mv squared, which is 1/2 times the mass of the car times that. So 50 times 25, 500 I meant to do. Right, half of 1,000 is 500 times 25 squared is about, I'm going to call that 3.1 times 10 to the 5th joules. And then if we want to know about power, we divide by the time. So power is equal to 3.1 times 10 to the 5th joules divided by 6 seconds. That's about 52,000 watts. And then if you want to convert it to horsepower, divide that by 746. So about 70 horsepower. All right. Your electric utility company sends you a monthly bill informing you the number of kilowatt hours of energy that you use that month. And that is something we talked about in the notes. What's a kilowatt hour? Determine how many joules equal 1 kilowatt hour. We did that in the notes. I'm just going to go through that again here. A kilowatt hour, that's 1 kilowatt times 1 hour. A kilowatt is 1,000 watts. That's what kilo means. And an hour is 3,600 seconds. And a watt is a joule per second. So that's 3.6 times 10 to the 6 joules. 3.6 million joules. A frost-free 17 cubic foot refrigerator freezer uses energy 500 watts, so that's 500 joules per second. That's what that means, right? When you hear the compressor running. If the fridge runs for 200 hours per month, how many kilowatt hours of energy does the refrigerator use each month? Two different ways to do this. You could figure out how many seconds this is, multiply by that, and then divide by the number of kilowatt hours, or joules in a kilowatt hour, which is 3.6 million. I'll do it that way for you. So 200 hours, how many seconds is that? 200 times each hour is 3,600 seconds. So that's 720,000 seconds. Power is equal to energy divided by time. So that means that energy is equal to power times time, right? That's basic algebra, just multiplying that by, multiplying the T up there. So the power rating of this is 500 watts times the time is 720,000 seconds, and that's equal to 3.6 times 10 to the, let's see, that's what I'm looking at here. 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8th joules. And how many kilowatt hours is that? Well, this is 1 kilowatt hour, so I just have to divide this by 3.6 times 10 to the 6, and that's just going to give me 100. So 100 kilowatt hours. That's one way to do it. The other way, maybe easier, is just turn these things into kilowatts and hours and then multiply them together. This is already in hours, and 500 watts is equal to 0.5 kilowatts, right? Move the decimal 1, 2, 3. So 0.5 kilowatts times 200 hours, kilowatt hours, 0.5 times 200 is 100 kilowatt hours. So same answer either way. All right, in the St. Louis area, off-peak electricity rates range from 3.2 cents to summertime rates of 7.8 cents. Is this true? Does the cost of energy really change? Yes, it does. So that's cents per kilowatt hour, and I'm buying 100 of them. So I just have to multiply these prices by 100, right? So it'd be 320 cents, which is $3.20 to $7.80. Right? And you're like, oh, that's so cheap. Well, that's just one appliance. So, you put all the appliances in your house together and you get an electricity bill. That's more than $7.